Hi, welcome back. So, what we kind of did in the last couple of modules is basically we're trying to use the boundary layer equations and apply it to a flat plate, right? So, where we stopped was essentially, we have the dimensional form of the boundary layer equations, right, which we are now using. So, this is the basically the dimensional form of the boundary layer equation. So, this is the x momentum and this is the continuity equation, and we are basically using a similarity variable, which is say this eta, and we're going to use that, right, with which we've come up with basically this is eta, right, given by equation 2, and we're going to use that, right, given into the equation, into the and we are using a definition of a stream function which is given by Shai here, and so that we can write the velocity u as this, right. So, what we did for the first time is that take term 1 of the x momentum equation and write that in terms of the similarity variable, and what we came up with was that u del x, right, can be represented in this form. So, we got x. So, u del x basically is a function of x, eta, f dash and f double dash, right, and f dash essentially means del f, del eta, and del 2f by del eta 2 is f double dash, right, and f is basically the non-dimensional stream function, right. So, let us continue to do this and also work on the second term, which right here, so we are done with the first term here. So, we are going to do the second term, right here. So, term 1 we are done with that. So, let us do with term 2, okay. Okay, so what we have here is v del u del y, right. Now, this is equal to del u del y. So, this is eta u infinity 2x, right, eta f dash minus f del eta u infinity f dash del eta del y. Okay, so now it's important that I think that you should be able to figure out what I did here. I'm not going to elaborate anymore. So, u is something that we found out, using the phi like this, and so what is v? So, v is nothing but, so v is nothing but minus del psi del x, right. So, if you do that, you should be able to get using this psi function, you should be able to understand what's going on here, right. Please do that yourself. And the second thing is u, okay, u is u infinity f dash eta. So, basically what we need del u del eta. So, again that should be del eta, yeah. So, that is del eta of u infinity f dash and del eta del y. So, if I do that, okay, what we will get. So, if I am going to expand this a little more, right, if I were to write this, if you see, so this del eta del y. So, let us see what we get here. So, this is Okay, so del eta, so it's u infinity, right, and f double dash, right. U infinity is a constant, take that out. So del eta of f dash is nothing but f double dash. Okay, into del eta del y. Okay, what is del eta del y? So because eta is this, right? So del eta del y is nothing but the term inside the root. So all we get there is u infinity by 2 nu x, right? So if I do that, so you can see that therefore, okay, v del u del y is equal to, okay, u infinity squared, right, by 2x, right, because the nu cancels out, okay, eta f dash minus f into f double dash. Okay, so that is essentially my second term. Okay, now let us go to the third term. So the third term is nu delta u del 2u del y2. Okay, so if I have to do this, the third term, it's nu del 2u del y2, right? Now this is again is equal to nu, right, del y. I will kind of request you to do this yourself. Okay, I think you can explain yourself. Okay, so del y of basically del u del y, right? Do we have a term there, del u del y? Okay, so that is nothing. So, well, let's write it like this: del eta of u infinity f dash, right, del eta del y. Okay. Okay. Now then this is equal to, so then this is equal to nu del y. Okay, yeah, so the term inside the bracket is nothing but u infinity f double dash, okay, and del eta del y is nothing but u infinity 2 nu x. Okay, then again this is equal to nu, I'll take the u infinity out, u infinity, right, into u infinity 2 nu x. Okay, so del y of f double dash. Okay, so that is del eta of f double dash into del eta del y. Right, makes sense? So the way I got this term, right, is basically first I took the u infinity outside of the bracket, so which comes here. So I got essentially I got del y of u infinity f double dash. So that boils down to del eta of f double dash into del eta del y. Okay, so therefore this okay, or nu del 2u del y2 is equal to nu u infinity 2 nu x, okay, this is f triple dash into u infinity 2 nu x, right. So, that is this, okay. Okay. So, well, so therefore, this becomes kind of easy, or nu del 2u del y2 is equal to, u cancels out, so u infinity square, okay, by 2x, right, by 2x, okay, f the third derivative, okay. Let's see if that is what I get, okay. So, now, yeah, so that's my term basically, okay. I think that's what I get, okay. So, nu del 2, yes, so this term is basically, so this u infinity square and nu cancel out 2x and f triple dash, okay, that is fine, okay. Okay, so now, okay, I have this, in case, see, this is the important part here, the v term, right. I do have the, elaborate, like, you know, the velocity, the working out of this. So, I would suggest that do this yourself, okay, get some practice, do this yourself, and however, I will post this, okay, I am not going to spend time on this right now doing it. So, since I have it, I will post it, okay, for you to kind of look at it if you need any help, but I would really suggest that, you know, do the math yourself, okay. I mean, this is all you have to do. So, remind yourselves or revise your calculus knowledge and do that, okay. I think it is useful, okay. So, right. So, now, so that's what we get the equation. So, therefore, we've got here, okay. And so, these are the three terms of the velocities, okay. And this v term, okay, v, because we've got the value of u, okay, we've got an expression for u, which is u infinity f dash, isn't it? But we do not have anything for v. Now, this v is essentially, you should be able to get that from the stream function in this particular case, and this actually boils down to, this v boils down to this. So, v is equal to by 2x eta f dash eta minus f of eta, okay. Or basically you can just say that v is equal to nu u infinity by 2x, okay, eta f dash minus f, right. So, that is also something which is important to know. So, how did I get this? Well, I basically carried out this differentiation, okay. So, I would suggest you please do it yourself, okay. All right. So, that is for v. Now, we need to convert some of the boundary conditions as well, okay. We shall convert these to boundary conditions. So, well, you know, the boundary conditions were something that right. So, we have the boundary conditions. Now, at y is equal to 0, u is equal to 0 and v is equal to 0, right. So, when I say convert these also to the similarity variable, so basically now you know what exactly how does this relate, because now I have converted my equations to f and eta and x, right. So, then what do I do now? So, therefore, now if you see eta, right, so the value okay. So, this is essentially your eta, right. So, this equation 2. So, eta is a function of x and y and u infinity and kinematic viscosity, right. So, eta is now given like this. So, what you see here is that at y is equal to 0, eta is 0. If you see here from 2, that even at y is equal to 0, eta is 0. Okay. So, essentially this means that here eta is 0, right. And if eta is 0, what is u? Okay. U is u infinity f dash eta, right. So, now eta is 0, so f dash is also 0. Okay. So, u is also 0, right, and f dash eta is also 0. Okay. So, eta is 0, right. So, u is 0. Well, so at y is equal to 0, eta is 0, okay, and u is 0. Okay, let me put it this way. Now, this is where is my, okay, 2. Okay. Now, let us put it this way. What does y is equal to 0 mean? What it means is that from expression 2, what we get is eta is 0. Okay. Then what we will do is we will go to u. Okay. Then what we will do is we will go to u, and what this means, right, from the term 3, right, what this means that f dash eta is 0, right. So, if you go to the expression in 3, u is 0, right. So, that essentially means that f dash eta is also 0. Okay. And again, so we have an expression for v, which is this here, right, which is this. So, v is also 0. So, if v is also 0, what you get that is that f is also 0. Okay. So, well, because in this term, in this expression, right. So, now what I essentially have is that v is 0. Okay. So, so let us write this as an expression. So, this is 4. Okay. So, from the fourth expression, right. Okay. So, what was this about? Okay. So, from 3, what you come to know is this, and from 4, what you come to know is that, well, at v is equal to 0, right, here y is also equal to 0, so eta is 0. So, what you get from here is that f dash eta is also 0. So, this is how you convert the boundary layer, it's a boundary condition, okay, at y is equal to 0. So, essentially what that boils down to is that at eta equal to 0, oh sorry, this is f actually, okay, this is f. So, f is equal to 0, right, and f dash is also equal to 0. So, this is my condition, okay, the boundary condition. Then again, the second boundary, another boundary condition is that at y is at y basically at far off, right, u is the free stream, right, u is the free stream. So, now at y is equal to infinity. So, if y is very large, so what do we get here for eta? If you see, now eta is also very large, right? If y is very large, eta is also very large. So, what I can say is that this essentially means, from 2 that eta also tends to infinity. Eta is also very large and u is equal to u infinity, right. So, if that is so, so if you see here from 3, if u is equal to u infinity, then f dash is equal to 1, right. So, it actually takes a constant value, right. So, therefore, what I get here is that this, right, from equation 3, it basically means f dash of eta is equal to 1. Okay. So, so therefore, the next condition is that eta tends to infinity, then f dash is equal to 1. That is very interesting, isn't it? So, basically what we are saying is, so if you go from eta of 0 to a very large number, your f is starting value of f, or f at eta 0 is 0, right, and f dash at 0 is 0 and f dash at infinity, or the final, or the end value of eta is 1, right. Okay, so f dash goes from 0 to 1, right, whereas f is 0 at the starting location. Now, so what you see basically that what we have done, right, in terms of the equation here, right. So, if I sort of transform this equation using these conditions here, we shall sort of put that together. Okay, let us do that. So, if we put this together, right, boundary layer equations. So, let us see. So, u del x, okay. So, u del x is this term here, okay, this term there. V del y is this term here, okay, and is equal to nu del 2u del y2, which is this term here, right. So, if I add those three, right. So, if I add those three, so therefore, the boundary layer equations, right. So, that becomes, so if I were to write it, it is 2x eta f dash f double dash plus u infinity square 2x f of double dash eta f dash minus f is equal to u infinity square 2x f triple dash, right. If you see this, so then what you can see is that basically you can get rid of u infinity square by 2x throughout, if you see, right. So, this bit can be cancelled out. So, then what I get from here is minus eta f dash f double dash plus, okay. So, I am going to expand this, eta f dash f double dash minus f double dash is equal to f of triple dash, right. So then, so therefore, you can see here that the first two terms cancel each other out, right. So this basically cancels each other out. So what we are left with, right, what we are left with is f triple dash minus f double dash is equal to 0, right. Now, so which is so interesting. I mean, if you were to now look what we from where we started and what we've achieved, it's very interesting. Let me come to this. Now, there's another thing still to be done. Again, I would leave you to do that, work that out for yourself. However, I will post it. I will post the working out of it. Okay. Now, because what we have not done so far is the continuity equation. So we've got del u del x, right, plus del v del y is equal to 0. Now, what we need to do is basically, check that if when you replace del u del x and del v del y with, your f and eta in terms of eta, so these two terms basically add up to 0. So you need to check this. So do this yourself. With whatever we've done so far, this should be useful. So go ahead and do that. Now, what is interesting is, let me actually write that down. Where we started out, where the Navier-Stokes equation, right? From there, we reached del u del x plus v del u del y is equal to nu del 2u del y2, right. And we have del u del x plus del v del y is equal to 0. This is my equation, right. This is the equation, and I use the similarity variable. Okay, I use the similarity variable eta, and then I come up with, so I come up with f with this, right. So essentially what we've, if you can see, so where we've landed up, so first we went with the Navier-Stokes equation, right, and we did a lot of, so we non-dimensionalized it. We used physics and knowledge of the boundary layer, basically boundary layers, right? And then we came up and we were able to write this down, the equations in non-dimensional form, which is applicable at the boundary layer, right? And after that, we put it back, the non-dimensional equations, we put it back to the dimensional form, so that we can, apply it to a flow regime where it goes from laminar to turbulent, okay. So we wanted to use a dimensional form of the velocities, which we did, right. So right at the first instance, the moment we take, you see there is no pressure term, right. So mathematically that boils down to that the unknowns are basically the components of velocity u and v, and the pressure term is not there. So we went ahead further, and again we used the concept of similarity, right, in the boundary layer, where we said that that the flow at, say, location x1, right, multiplied by a certain scaling factor represents exactly the flow at x is equal to x4, right. So that was, so basically we said the flow is similar, right. So when we say that the flow is similar, so we use that information and that knowledge, and then again introduced a similarity variable, okay, which is eta here, right? And then yeah, so eta, and then we came up, we also defined a stream function, right? And from there we were able to transform our basic equations, okay, into using the similarity variable. So the moment I did that, I came up finally with this equation, right, with this equation. So what we have essentially done, right, is taken number one, okay, what we've essentially, let me sort of write that down. So what we've done is taken two PDEs, like two partial differential equations, right, and converted them to one ordinary differential equation. So that is basically a numerical simplicity. It is easier to solve, that's all. Okay. So therefore, we've taken two PDEs and converted them to one ODE using the similarity variable, right. And this is, of course, it's a nonlinear ODE, and yeah, it's of the third order, right. So because you have f d3 f d eta 3, okay. Now what we will basically do is that using the boundary conditions that we have, right. So let us call this equation as this equation, okay. So this equation, let us number it. So we're going to number this as 4, right. This is 4. So, and also these are my boundary conditions. So this is my boundary condition. So I'm going to call this as 1, and this is 2. So therefore, equation 5, okay, equation 5, which is basically this equation here, right, plus boundary conditions 1 and 2 can be solved to represent the system completely, right, to represent the system completely. Now, so we will stop here, and what we will do in the next module is to go and see. So now, how we do this? Well, basically, we go ahead and write this out as a computer code, and then we solve it. Okay. So I have done that, and again, well, let's talk about that in the next module. So we will stop here for now. Thank you.